Welcome to AI Paper Podcasts, your shortcut to understanding the latest research. Today, we're tackling BLIP3o-NEXT, next frontier of native image generation. This is a big one, a fully open source foundation model that's aiming squarely at, well, two of the toughest challenges in visual AI, top-notch image generation and really precise image editing.
It really is a significant paper. And, for those of you who want the quick summary, we can actually give you the 4 key insights right up front. The authors didn't just build another model. They laid out a kind of roadmap.
Okay, perfect for our quick summary then. Let's hear them. Yeah. What did they find was really decisive?
Right. First, and this might surprise some people, architecture itself isn't the main differentiator. They found most designs are kind of comparable. What really matters is efficient scaling and getting that inference speed up. Practicality.
Interesting. Okay, point 2.
Second, and this is pretty exciting, reinforcement learning. When applied very specifically, gives a major boost to generation quality, especially for things like getting legible text inside the image, which is notoriously hard.
Right, the instruction following aspect. Okay, third insight.
Third, they made real progress on image editing consistency, keeping the original image intact while making the requested change, that tricky balance. They found it's best improved through specific post-training tweaks and, crucially, some clever engineering using VAE features. Low-level stuff.
Gotcha. And the final one, probably not a huge shocker.
Yeah, the fourth is almost a universal law for these big models. Data quality and sheer scale are still the ultimate performance ceiling. You can't escape that.
Okay, so that's the high-level view. Our mission for the rest of this session is to really unpack this thing, look at their novel hybrid architecture, figure out why their RL approach works so well, and understand the technical tricks they used for that editing consistency.
Exactly. The core idea is this unification, right? Text to image and image editing, all handled by one efficient system.
Let's dive right into that architecture then. It's a hybrid, autoregressive, or AR, combined with diffusion. Why this mix? Feels like pulling from different schools of thought.
Well, it's really about getting the best of both. The goal is to merge the semantic understanding and the, let's say, instruction-following capability of large AR models. They're like the planners with the incredible fine-grained detail, the photorealism that diffusion models excel at.
So the AR model, which they kicked off using the Qwen 3 architecture, I believe acts as the sort of high-level planner and instruction interpreter. What does it actually output?
So AR part takes your input, which could be text, maybe a reference image for editing, or both. And the crucial part is it predicts the next token, but not as a continuous value. It predicts discrete image tokens.
Discrete tokens, it feels like a key point. So the image gets encoded first, maybe using BLIP3o, and then quantized into a limited set, like 729 tokens for a decent-sized image. Why go discrete there?
That discreteness is really the bridge to efficiency. When you're working with discrete tokens, you can tap into all the existing tools and methods built for large language models. Think about the RL phase later. It makes it so much easier to apply techniques we already understand well for language. It connects visual policy to language policy tools.
Okay, that makes sense. It streamlines the optimization later. So the AR model outputs its plan as these discrete tokens, and then the diffusion transformer, the DIT, steps in.
Precisely. The DIT uses the final hidden states from those predicted discrete tokens as its main conditioning signal. It's not starting blind. It uses that semantic map from the AR model to guide the diffusion process, generating the final high-res VAE features that become the image.
And the whole system, the planner and the renderer, they're trained together, right? Using a joint objective function, something like L equals LCE plus lambda times LDiff. For our technical listeners, what does that combination actually achieve?
It's all about balance. The LCE, the cross-entropy loss, pushes the AR model to predict the right discrete tokens accurately, making sure it follows the instructions and gets the semantics right. At the same time, the LDiff, the diffusion loss, ensures the DIT produces a clean, high-fidelity final image. So you're optimizing for both clear instructions and good-looking pixels.
Right, clarity and quality. Now, you mentioned the parameter count is around 3 billion total. That seems efficient, maybe. Usually, instruction following and reasoning scale hard with model size. Are they compromising here, or do they think 3B is genuinely enough?
That ties back perfectly to their first insight. They explicitly argue that model effectiveness isn't just about size. It's heavily dependent on efficiency and inference speed. They found that simpler, scalable architectures use the established backbones like Qwen 3 and Santa 1.5 that allow for fast inference are often more effective than slightly better but much slower, complex designs. Then compared to giants like GPT-4o. This 3B model is kind of positioned as a performance per watt sweet spot.
So a robust, efficient structure. But structure alone doesn't always get you state-of-the-art quality, especially on complex prompts. Which brings us to reinforcement learning. How did they use RL to push beyond that initial training?
Yeah, RL comes in after the main training. It's a post-training stage, specifically aimed at improving performance on tasks, where standard supervised training often falls short. Think complex instructions, getting text right, placing multiple objects correctly, things that are easy to verify.
And you mentioned earlier they only applied RL to the autoregressive model, the AR part. Why just the planner and not the diffusion renderer?
Because the AR model is the one generating those crucial discrete tokens that define the image's core structure and meaning. If you optimize the planning policy, the diffusion model just executes a better plan. And technically, it's way easier. Applying RL to discrete tokens lets them use all that existing RL infrastructure built for LLMs. Much faster, much cheaper to implement.
That's a smart move, leveraging existing tools. Okay, let's get specific. The mechanism they use is called Group Relative Policy Optimization, or GRPO. How does that work?
Okay, GRPO. It's a pretty neat policy optimization method. So the AR model, which is the policy we're tuning, samples a group of possible outputs, basically different sequences of those discrete image tokens. Then a frozen diffusion model takes each of these token sequences and decodes them into candidate images.
So you get a bunch of potential image results based on slightly different plans. Then what?
Then a reward function kicks in. This function has to be verifiable. So for text, they might use an OCR metric to see if the text is readable. For object composition, maybe something like unifies to check if the objects are there and related correctly. This function scores each candidate image.
Based on how well it met the specific goal.
Exactly. And then the optimization happens. They adjust the AR model's policy to increase the chances of generating token sequences that lead to high reward images. They use a KL divergence penalty too, just to make sure the policy doesn't change too drastically and become unstable.
And did it work? What were the results?
Oh yeah, the quantitative results are quite clear. On tasks like composing multiple objects accurately, evaluated with Genevil, the GRPO-tuned model hit a score of 0.91. That was noticeably better than prior models, which were typically stuck below, say, 0.88.
That's a solid jump.
It is. And qualitatively, you just see it. Look at the examples for text rendering before GRPO. Asking for text on a sign might give you blurry nonsense. After GRPO, it's often sharp and legible, like text on road signs or stamps in their examples.
That really confirms that tuning the discrete token generation via RL is effective for these tricky compositional tasks in this kind of hybrid model. Okay, let's switch gears to the other major challenge. Image editing consistency.
Right. This is always tough. You ask the model, make the cat blue, but you want the couch it's sitting on, the lighting, everything else to stay exactly the same. Standard vision encoders often lose that fine-grained detail.
So how did BLIP3o-NEXT tackle this? They seem to have a couple of strategies. Strategy one sounded pretty foundational, multitask training.
Yeah, that's about building it into the training data. They specifically included an image reconstruction task. Basically, they feed the model the reference image and just tell it, keep the image unchanged. Forcing the model to learn perfect reconstruction helps enforce fidelity later during actual edits.
Makes sense. Train it to copy perfectly before you ask it to change things subtly. But the really novel part, the technical trick, was strategy 2, VAE Latent Conditioning. Can you break that down?
Okay, so the idea is the semantic tokens from the AR model capture the what, but not necessarily the how, in terms of exact pixel details. To preserve those details from the original image during an edit, they needed to inject low-level information. That's where the VAE latents come in. They contain fine-grained details from the reference image.
So they're adding back the detail that the high-level plan might miss. How did they inject it?
They tested two main ways to feed these VAE features into the diffusion model, the DIT. Let's call them Method A and Method B.
All right, Method A.
Method A involved adding the VAE features as extra inputs to the cross-attention layers inside the DIT. So the DIT gets the semantic instructions from the AR model via attention, and it also gets these VAE features, sort of flattened and projected, also through attention. It's like giving the DIT both the edit instruction and a detailed reference manual of the original textures and colors it needs to pay attention to.
Okay, so Method A enhances the instructions given to the DIT, What about method B? That was noise space injection.
Yeah, that's quite different. Instead of feeding the VAE features into the attention mechanism, they concatenate the VAE features directly with the random noise tensor that the diffusion process starts with. It's like altering the initial canvas before the DIT even starts denoising.
Interesting analogy. So method A is like better instructions. Method B is like constraining the starting point itself.
Pretty much. And the really key finding, combining both worked best. Giving the DIT the detailed VAE info via cross-attention and injecting it into the initial noise space yielded the highest visual consistency in the final edited image.
That dual conditioning approach sounds powerful. And that's what let their 3B parameter model compete with much larger models like Bagel or Omnigen 2 on editing benchmarks like IMDidIt.
Exactly. It performed comparably, which is impressive for the size. They did mention a small caveat, though. The VAE decoder they used has a downsampling factor of 32. That compression saves time, it's fast, but it means some very fine pixel details are lost. So there can still be tiny inconsistencies compared to the original reference. It's that classic trade-off, speed versus perfect fidelity.
Always a trade-off, isn't it? So looking ahead, did the authors point towards specific next steps beyond just making the model bigger?
They did. One area is designing better system prompts, ways to tell the model clearly whether you want it to do in-painting versus changing a subject, because those might need different internal settings. They also mentioned prompt rewriting, maybe automatically enriching the user's prompt to get better results. And the big one.
Let me guess, RL for editing.
You got it. Applying RL specifically to improve editing consistency. But that's really hard because you need a much more sophisticated reward model than just checking if text is readable. How do you automatically measure if the rest of the image stayed consistent? That's a tough reward design problem.
Okay, let's quickly recap the big contributions here. We've looked at BLIP3o-NEXT, a model series known for its commitment to open source.
And its main technical achievements are really threefold, I'd say. First, this novel autoregressive plus diffusion architecture that's built for scalability and speed. Second, the smart use of RL, specifically GRPO on the discrete AR tokens, to really boost quality on hard tasks like text and composition.
And third, that systematic approach to image editing consistency, figuring out that injecting VAE features via both cross-attention and noise space conditioning is the way to go.
And crucially, they didn't just write about it. True to the BLIP3 philosophy, they released everything. The model weights, the code, even their cleaned training datasets, BLIP3o pre-train and BLIP3o 60K. That openness really helps push the whole field forward.
Absolutely. So, for the final thought, the provocative takeaway for you, our listeners, it comes straight from the paper's conclusion. They suggest the biggest hurdle moving forward isn't necessarily finding a better architecture or just scaling up parameters.
No, they pinpoint the core challenge now as being about metrics, designing really effective reward models. How do you create a reward signal that simultaneously captures and correctly balances image quality, how well the image follows the instruction, and that fuzzy thing we call human preference? Especially when these goals sometimes conflict, that comprehensive reward function is still the missing piece.
It's fascinating. The bottleneck isn't just engineering, it's almost philosophical. How do we objectively define and measure good in a way a machine can optimize for? A great point to ponder. Thank you for tuning in to this AI Paper podcast on BLIP3o-NEXT.